morning. In the last classes, we have derived the first and second TDS equations and its applications. Today we can move into the last section of the module, that is Clausius-Clapeyron relation. This equation is an equation used to obtain the change of pressure with temperature for first order phase transitions. So we have to deal with the first order phase transitions here. So what are the conditions for a first order phase transition that we have to look into? During phase transition, the temperature and pressure is a constant. There will be two phases during the phase transition, not at the phase transition, during the phase transition. Example, if we are heating a liquid, so it is while heating at 100 degree, if it is water at 100 degree, the water starts to vaporize. But you can see that the water all the water is not vanishing or vaporizing at the same time, but it gradually transformed into vapor. So two phases are present. So before phase transition, before phase transition only one phase is present. After phase transition only one phase is present. During phase transition, the one phase is gradually transferred to the other phase. So during the phase transition, temperature and pressure is a constant, but the entropy and the molar volume may change. Molar entropy and molar volume, or entropy and volume may change. So we can start with the equation, start with such statements or such a criteria. First order phase transitions. We can derive Clausius Clapeyron equation. So we have to deal with the first order phase transitions. So Clausius-Clapeyron relation is for first order phase transition. So we can consider SMI. This is the molar entropy. SMI is the molar entropy of the initial phase. VMI is the molar volume of the initial phase. SMF is the molar entropy of the final phase. VMF is the molar entropy of the molar volume of the final phase. So during phase transition, P and T are constant. So like there are n0 number of moles initially present. There are n0 number of moles initially present. And a fraction of these n0, that is x, fraction of n0, that is transformed into the second phase, that is the final phase, at a particular moment. So x is the fraction of this n0 that is transformed into the final phase at a particular moment. So we can write the total entropy of the system. The system is now contains both phases, the initial phase and the final phase. So because all the initial phase, all the moles in the initial phase are not transformed yet, so it gradually transformed into the second phase. So what we can write? S is equal to N0. This is the total number of moles. So X is already transformed into the second phase. So remaining is 1 minus X. So the fraction is N0 into 1 minus X, that is N0 minus Nx. So N0 into 1 minus X into Sm initial plus N0 into X. This is the fraction of N0. So the total number of moles is N0X into SMIF. This is the total entropy at a particular moment since both the phases are present. Similarly, we can write the total volume as N0 into 1 minus X into VMI plus N0 into X into VMF. These are the two equations that we can obtain. That means this S and V are linear function of X. This depends linearly on the number of moles. The fraction of the total number of moles. So if the phase transition occurs at a constant pressure and temperature, so we can write the molar enthalpy equation as, that is dH. So we have the equation for dH is TdS m plus VdP. But this is at constant pressure. The phase transition occurs at a constant pressure. So we can write this as T into ds. ds is Sf minus Sf. Sf minus Sf. That is dH. Molar enthalpy dH. And also we can write the Gibbs energy. You know that we have already discussed earlier that the Gibbs energy is a constant before and after. So for the initial phase, there is some Gibbs energy, that is G dash if it is solid. So G double dash for liquid. So before phase transition, the phase is having a molar Gibbs energy as G dash, and after the phase transition, it is having the entropy, it is having the Gibbs function as G double dash. Then G dash is equal to G double dash, that we have already discussed while taking detailing about the Gibbs function. So we can write the Gibbs energy equation here also, that is dG, that is molar Gibbs energy, minus SdT plus VdP. So we can write at constant temperature, we can write the equation. At constant pressure, we can write the equation. So at constant temperature means this will goes to 0. So Vm is equal to, at a constant temperature, Vm is equal to dou G by dou P at T, and at constant P, we can write, at constant P means this will goes to 0 and this will be there, that is S is equal to, Sm is equal to minus dou G by dou T at P. So these are the two equations. That means this Gibbs energy can be a function of pressure at a constant temperature and this Gibbs energy can be a function at constant temperature, that will be the molar volume, and the Gibbs energy can be a function of the temperature at constant pressure, that will be the molar entropy. So these two values, this molar entropy and this molar entropy and molar volume will change for a phase transition, that there should be some change during the process. So the first order phase transition means we can define a first order phase transition. For a first order phase transition, it satisfies two conditions, that is, the molar volume and molar entropy should change. The first order derivative of the Gibbs function. The second criteria is the first order derivative of the molar Gibbs function changes discontinuously at the phase transition. So there are two criteria that should satisfy. If these two criteria are satisfied, then we can say that that will be a first order phase transition. That is, the molar volume, that is Vm, and molar entropy should change. The first criteria is there is a change in V, that is molar volume. There is a change in Sm, that is molar entropy, and Vm, that is molar volume. Second one is the first order derivative of molar Gibbs function changes discontinuously. So if any change, any transition or any transition which satisfies these two criteria, then that transition is known as first order phase transition. So these are the equation, this you will get from the Gibbs energy equation. So during phase transition or at phase transition, this Gibbs function change abruptly. The first order derivative of the Gibbs function, that is this dou g by dou p or dou g by dou t, will change discontinuously. It is not a continuous change. At the phase transition, there is a discontinuous change, or there will be a discontinuity at the first order derivative. That is for these two values. So we can draw the different graph, the dependency of this Gibbs function. Then we can draw the Gibbs energy for a phase transition, and these two values, that is the first order derivative of Gibbs function, and also we can draw the graph for the specific heat capacity at constant pressure. These four plots we can draw for a particular phase transition. So the first graph is, this is G, that is molar Gibbs function with the temperature. So this is vaporization, for vaporization, that is from liquid to vapor. I am drawing all these figures. This is the temperature at which the phase is the first phase is transformed into the second phase. That is this phase I. This is the phase F. So there is because the Gibbs function will change like this during, this is the liquid actually, so this is the vapor. So the Gibbs function, the value of Gibbs function with respect to temperature is like this. minus dou G by dou T at constant P. That is actually the molar entropy. This is with respect to T. That means we can see that the second criteria is this first order derivative of this function varies discontinuously. So we can write this, that is minus dou G by dou T. So taking this derivative from here, that is minus dg by dt from this, you will get there is a discontinuity. So this is the temperature, the transition temperature. So this is actually molar entropy. This is for phase 2 and this is for phase 1. So this is phase F and this is phase I. You can see that there is a discontinuity at this point. So at this point there is a sharp change. So up to this point there is a slope and up to from this point there is another slope. So this will change discontinuously. The fourth one is dou G, third one is dou G by dou P at T. That is actually the molar volume. So there is also a discontinuity. There is also a discontinuity here. This is phase F and this is phase I. This is actually molar volume. So here also the first derivative change abruptly or discontinuously. So the fourth block is for Cp. You can see that Cp is nothing but E into dou S by dou T at P. So dou S by dou T at P means from this graph. This is actually S. So this is there is no change in the temperature during this process. Here and during the phase transition, there is no change in the temperature and the pressure is also a constant one. So this is molar entropy. So we can take this molar entropy here. Dou Sn by dou T means this will goes to infinity. Even though there is a change in the molar entropy, there is a change in the molar entropy during the phase transition. This term will goes to 0 during the phase transition. dt is 0. So this total value will goes to 0. This is actually the molar heat capacity at constant pressure. So the graph again we have to take the derivative of this one for taking the Cp. So you will get for Cp, but this will goes to infinity. This is phase F. This is phase I. This is for molar heat capacity. Molar heat capacity at a constant pressure, that is Cmp. So these are the four plots for this. This is the first order derivative. These two graphs represent the first order derivative. This is for molar this function. This at during the phase transition. This is the pointer. There is a kink. Here there is a jump. Here there is a jump. Here also there is a jump. But this is at infinity. Goes to infinity. That means during the phase transition, for this value, for phase I, there will be a constant Cp. Means the Cp is very small, there is only a little change. Here also there is a little change. But during the phase transition, since two mixtures are present there, this phase I and phase F are present at this phase transition temperature. So for this mixture, the Cp will goes to infinity. The value of Cp will goes to infinity. That is the meaning of this fourth plot. That means for that, when at that particular temperature, when P is is a constant, dt is 0, and when t is a constant, dp is 0. We can write Cp, that is molar heat capacity, as T into this same equation, T into dou Sm by dou T at constant pressure. So at constant pressure this will goes to 0, so this will go, the value will goes to infinity. Similarly, the volume expansivity, that is 1 by Vm into dou Vm by dou T at constant pressure, so this will goes to again infinity. And this isothermal compressibility, that is only for in the case of first order phase transition, these conditions 1 by linear are satisfied, or these equations we will get only for first order phase transition. For second order and higher orders, these things will so at constant T. So this is only for first order phase transition. So this will again goes to infinity. So these terms will goes to infinity during the phase transition. We can consider the second TdS equation, that is TdS equal to the molar heat capacity Cmp into dP minus T Vm beta into dP. So you can see that during the phase transition dt will goes to 0 and Cp will goes to infinity. This beta is also goes to infinity. This dP is 0. So we cannot do anything with this, the second TdS equation. This is the second TdS equation. So we cannot do anything with this second TdS equation, but we can integrate the first TdS equation to some extent. That is, for first TdS equation we can write first TdS equation, that is TdS equal to Cmv molar heat capacity minus plus T into dou P by dou T at constant volume into dV. This is actually dP by dt, that is, there may have various P's and T's at which the phase transition occurs. So we can say that the pressure is a function of temperature only, and which will obey certain equations in which the P is a function of T only. So we can write some equation relating to that from this equation. So we can write this is T into, this is some SF minus SI, which is equal to, this dt will goes to 0, of course, during the phase transition. This dt will goes to 0. So we will have T into, since this is a function of T only, we can write dou P by dou T at Vm as dou dP by dt. Then Vm as Vmf minus Vmi. So dP by dt is equal to, dt will get cancelled, dP by dt is equal to Sf minus Si divided by Vf minus Vmi. This m is, I am representing only the molar value. We cannot write small s and capital S like that. So I am using the subscript as m for for phase transition for molar entropy and molar volume. So this is equal to SMF minus SMI divided by VMF minus VMI. So this equation is known as Clausius-Clapeyron relation. That is dt by dt, which is equal to SMF minus SMI divided by VMF minus VMI, which is equal to HF minus HI. This is the molar enthalpy divided by T into VF minus VM. Since this S is equal to during the phase transition, B is a constant, so dH is equal to TdS. So dH is equal to TdS. So we can write this ds changing the molar entropy value as H by T. T is also a constant, so we can write the equation like this. This equation is known as Clausius Clapeyron equation. So this will get the change of pressure with the change of temperature during a phase transition. So this is the equation. It is connecting the molar entropy and molar volume. These two will change during a phase transition, and this we can connect to the molar enthalpy relation as this. So this is the Clausius-Clapeyron equation. This will apply only to the first order phase transition. So this H is also known as molar latent heat. So we have discussed earlier that during phase transition, this H is known as molar heat, latent heat, molar latent heat or latent heat. This enthalpy can be called as latent heat. So here it is molar latent heat. So we can also say instead of molar enthalpy and molar volume, we can write specific enthalpy and specific volume, etc. Divided by mass. That also is a valid equation. So here we are taking the molar enthalpy, molar volume, molar entropy, etc. for this equation.